Hello everyone, welcome to DSP NIT. I am M.Sushma Sai from ECE 3rd year. In this video, we will solve the example 5.4.1 in the book Digital Signal Processing by John G. Proakis. The given question is, the exponential signal xa of t is defined as e power minus t when t greater than or equal to 0, 0 when t less than 0. We sample at the rate f equals 20 samples per second and a block of 100 samples is used to estimate its spectrum. Determine the special characteristics of the signal xa of t by computing the DFT of the finite duration spectrum sequence. Compare the spectrum of the truncated discrete time signal to the sequence of the analog signal. Given that sampling frequency is equal to 20 samples per second, estimating block of 100 samples. By computing DFT of finite duration sequence xa of t, we get xa of f equals to 1 by 1 plus j 2 pi f. The exponential analog signal sampled at the rate of 20 samples per second yields the sequence x of n equals to e power minus n of t. That is equal to e power minus n by 20 when n greater than or equal to 0. That is equal to e power minus 1 by 20 whole power n. That is equal to 0.95 whole power n when n greater than or equal to 0. Now x of n is defined as 0.95 whole power n when n lies between 0 and 99. Otherwise, it's 0. Calculating the endpoint DFT for x of n, we get x of k equals to sigma k runs from 0 to 99 x of n e power minus j 2 pi k by n. K runs from 0 to n minus 1. To obtain sufficient detail in the spectrum, we choose n equals to 200. This is equivalent to padding the sequence x of n with 100 zeros. We get the spectrum as shown below. In this case, the DFT x of k bears a close resemblance to the spectrum of the analog signal. The effect of the window function is relatively small. Now, we will observe the magnitude plot in frequency domain by changing the number of blocks. Suppose window function of length L equals to 20 is selected. Then the sequence x of n is now given as x of n is defined as 0.95 whole to the power of n when n lies between 0 and 90. Otherwise, it's 0. Now, we get the spectrum as shown below. For this spectrum, we can say that there are more side lobes present. By observing these two magnitude spectra, we can say that as the number of samples considering decreases, approximation is more and the signal doesn't resemble the analog signal. Consequently, DFT is no longer a good approximation of the analog signal spectrum. Now, let's see the MATLAB execution for this spectrum. Plotting the given exponential signal e power minus t. And then plotting the magnitude spectrum. Now plotting the sampled signal x of n. Spectra for 100 samples. Spectra for 20 samples. After running, we get the spectrum as follows. Let us see this in detail. The first graph shows exponential signal e power minus t. The second graph shows magnitude spectrum. The third graph shows the sample signal x of n. The fourth graph shows the spectra for 100 samples. Fifth graph shows spectra for 20 samples. In this way, we can plot the graphs in MATLAB. Thank you.